Record to the cloud. Okay.
Are you recording already?
Yeah.
Okay.
Yeah, sure.
Okay. Welcome everyone. Today is Opar's final dissertation defense. He's been here for 4 years. And instead of giving you the document, that's what he did. And yeah, he's shooting for around 45 minutes. But feel free to ask questions at any time, anybody. But we will have time at the end of the presentation, specifically for people not on CARS committee. And then after that, we'll ask you to leave the room, and then we'll have a Q&A with just the committee and CARS. So that on CARS, the floor is yours.
All right. Thanks everyone for making time to attend my defense. So the title of my dissertation is Implicit and Deep Learning-Based Control Methods for Uncertain Nonlinear Systems. Just a second. Okay, so firstly, a bit of a background about myself. So I got my bachelor's in technology degree from IIT Delhi in production and industrial engineering in 2018. After that, I worked at IIT Delhi for 1 year as a research assistant. I got my master's degree last summer here from UF. And while working at IIT Delhi, I also received the award for the best bachelor's thesis in the Department of Mechanical Engineering. And these are the courses that I took here, controls related courses. Okay, and these are my publications. So this is the list of my journal publications. So as you can see here, there are 3 published journal papers, 4th journal paper that I submitted. All these are first authored papers. So the 4th first authored journal paper I submitted to Automatica. It is under review right now. And there are also 2 other papers, co-authored papers that are under review. And hopefully by the end of next 2 weeks, there will be 3 more papers on this list. And these are my conference publications. So 2 are first authored, and there are 4 second authored papers. So, and this is going to be the outline of my dissertation. So chapter 2 is about fully connected deep neural network based adaptive control. And chapter 3 is basically the extension for a broader class of neural networks called the ResNets. So I had presented chapter 2, 4, and 5 in my proposal as well. So I am restricting these presentations to chapter 3, 4, and 5 because the contents of chapter 2 are already encompassed by chapter 3. So to introduce the problem that I address in this dissertation, consider the control affine dynamic system given by these dynamics. X dot equals fx plus g times u. So where f is an unknown drift vector field. And there is also control effectiveness g, but for the sake of simplicity, I would not consider the g term in the rest of the dissertation. But the methods developed in this dissertation can also be extended for unknown control effectiveness case. Now, if the term f of x comma t could be known, we can simply use feedback linearization to address this. But the problem is F is not known. So we cannot just use feedback linearization. So what's the solution to this? The solution is that we can construct an adaptive estimate of F and just use that in our controller. And that's what the rest of the dissertation is going to be about. That's what the rest of this talk is going to be about. So chapter 2 deals with a deep neural network-based estimate of F using real-time weight adaptation laws for the DNN. Chapter 3 is going to be about ResNet-based estimate with real-time weight adaptation. However, deep neural network-based approaches are only applicable for time invariant systems, and this is because time does not necessarily lie within a compact domain. On the other hand, DNN-based methods require the compact domain assumption, and therefore, like we need different tools to deal with time varying systems. So in chapter 4, we have we consider a linearly parameterized model with time varying parameters, and then I design an adaptive controller for that to achieve asymptotic tracking. And chapter 5 is going to be about implicit learning with robust integral of the sign of the error controllers, that is the RISE controllers. So RISE controllers are a class of controller that have been known for like 2 decades, but the best known result for RISE controllers used to be asymptotic tracking, until my work where I showed that the tracking is not only asymptotic, but it is also exponential. So moving on to chapter 3, which is deep residual neural network, that is ResNet-based adaptive control, a Lyapunov-based approach. Now this work is under review at Automatica, but this was also presented at IEEE CDC last year. So again, consider the dynamic model given by these dynamics, but here F is not explicitly time varying. So and the objective is that we need to construct a DNN-based estimate of f of x, which is our unknown drift vector field. And the control objective is that the tracking error E should go to 0 as t goes to infinity, where xd lies within a known compact set. Now, to address this problem, a lot of offline training methods have been developed for DNNs. However, offline methods have their own challenges. The main challenge is that it is essentially open loop in terms of the weights. I mean, the weights need to be pre-trained. That is done after gathering some training data and then employing optimization techniques to minimize some loss function. But the weights do not adjust in real time. Moreover, it is not clear what kind of trajectories the system needs to follow such that we obtain a sufficiently rich data set. I mean, there has to be some kind of persistency of excitation condition to be satisfied so that the obtained data set is sufficiently rich. Moreover, this also often requires the knowledge of the state derivative, because in order to solve the regression problem, we need the knowledge of both the sides of the equation. And therefore, it is desirable to construct real-time adaptation methods for the DNN. So real-time adaptation method was first developed by Professor Frank Lewis. That was in 1996 for a single hidden layer neural network-based adaptive controller. But since then, extending this approach for DNNs with an arbitrary number of layers, that was an open problem. Until in my recent work, and which is also the chapter 2, I developed Lyapunov-derived adaptation laws for fully connected DNNs with an arbitrary number of layers. So I basically provide a general formula for the adaptation law for the DNN. Now the thing is, if we have a high dimensional system, for example, so the problem there is that we often need deeper neural network because the functions could be very complicated. And therefore, we need deeper neural networks. The problem with fully connected DNN architecture is that it is more susceptible to the problem of vanishing or exploding gradients. So I'll just explain this in the next slide, what happens here. So to explain that, let me just give a brief overview of chapter 2, where I developed the fully connected DNN-based adaptive controller. So for that, consider the DNN architecture given by this expression where VK, all these V's are basically the DNN weights. The lowercase V's are the DNN activation functions. And theta here is basically the vector of all the DNN parameters. That is, all of the DNN weights are vectorized and stacked together into a single vector. And then the control and adaptation law for this DNN is given by these two expressions. So these 4 terms here are kind of the standard terms that show up. And the last term, that is phi theta hat, that is the DNN-based adaptive feedforward term. And for that term, the DNN-based adaptation law is given by this expression for theta hat. So the proj here denotes the projection operator, and the projection operator is used to ensure that our weight estimates lie within a bounded set. And within this projection operator, then we have gamma, which is our learning rate. And then we have the Jacobian of the DNN with respect to the weight estimates, transpose times the tracking error E. Now, this expression looks simple, but the Jacobian has like a lot of computation required here. So like there is a bunch of notation here, but I will just briefly explain the problem, like how we have the vanishing gradient issue. So notice the product involving the V hats, which are our weight estimates, and V hat primes, which are the gradients of the activation functions. Now, what happens if we initialize V hats with small values? The result is that there would be a product involving all of these smaller values, and that would result in a very, very small value for the expression for theta hat. And what does that mean? That basically means that theta hat dot is practically 0. That means theta hat is not changing and there is no adaptation happening. So to address this, we can use the ResNet architecture instead of a fully connected DNN architecture. And I will explain that in the next slide. So how is the ResNet different? Why we do not have a vanishing gradient issue with the ResNet architecture? I'll explain that here. The difference is the difference between ResNet and fully connected architecture shown in the previous slide is that the ResNet contains shortcut connection. So shortcut connection is something, it looks like this. There is a shortcut across this fully connected DNN block. So if the input to this block is eta p, the output would be eta p plus phi p, which is the pth fully connected DNN block. And then there are multiple such residual blocks we can use, stack them all together, and that results in our ResNet architecture. So this architecture can be recursively represented using these expressions, where again, the pth fully connected DNN block is again represented using this recursive relation. And for this ResNet architecture, the adaptation law, this is the Lyapunov-derived adaptation law. I'm not getting into the Lyapunov analysis in the presentation for the sake of time, but this is what we have obtained after deriving the adaptation law from a Lyapunov-based analysis. So this is our expression for the adaptation law, where phi prime can be computed using this computation scheme. There is some math derivation for that, but I'll just explain what is all that's important here. So notice in this expression for phi p prime, there is an identity matrix term showing up here. And why does that term show up? That's because of the presence of shortcut connections in the ResNet architecture. The identity matrix term shows up here because the shortcut connection is essentially just an identity function, and the Jacobian of an identity function is an identity matrix. So that's why this term shows up here. Now, what happens if there are vanishing gradients in some of the fully connected DNN blocks that compose our ResNet? So let's see what happens if the psi L term, all of the psi L terms are 0 in this multiplication. We still have an identity matrix term that gets multiplied to this, and therefore phi p prime would be lambda p, and it would not be 0. But if we did not have shortcut connections, there would be no identity matrix term showing up here. And as a result, there would be a product involving all of these psi L terms. And if these terms are near 0, then phi p prime would have an extremely small value, and we would have the vanishing gradient problem. But since we have shortcut connections, we are able to overcome the vanishing gradient problem with the ResNets. And this is also something that we see in our simulation results, which I'll show next. So so for the simulation setup, we consider a 10-dimensional system and the function f of x, where A is a large matrix. It's 10 by 60 matrix with randomly selected elements, and yx is just a bunch of nonlinear functions. So f of x is a highly nonlinear function that we are trying to approximate. And we consider the reference trajectory involving these sinusoids. Now, the ResNet configuration that we select for our simulation involves 20 hidden layers, a shortcut connection across each hidden layer, and 10 neurons in each layer. And the results are compared with an equivalent fully connected DNN, that is a DNN with no shortcut connections at all. And for a fair comparison, the weights for both the DNN architectures are initialized using a Monte Carlo approach with 10,000 iterations to minimize this function. And here are our simulation results. So notice the plots of the weight estimate. So these are just arbitrarily selected weight estimates. So there are like about 2,000 total weights in the simulation, but we can only show the plot for a few. So notice the plots of the weights. The weights for the fully connected DNNs are not able to adapt at all. They're practically just constant. On the other hand, the ResNet weights are able to evolve, adapt, and converge to some values. And the result of that we can also see in our tracking and function approximation error plots. So as you can see here, the tracking performance with the ResNet architecture is much better than the fully connected DNN architecture. That is, the tracking error is able to actually converge with the ResNet. On the other hand, with the fully connected DNN, we are not even getting convergence. And the reason behind that is the ResNet is not even adapting. And we also see this for the function approximation error plots. So you can see here that the RMS tracking error and the RMS function approximation error is almost half that for the fully connected DNN, while both require the same control effort as seen here. So to conclude, a ResNet-based adaptive controller was developed for control affine nonlinear systems in this chapter. The ResNet provided twofold improvement in tracking and function approximation performance in comparison to an equivalent fully connected DNN. And I will explain the future work at the end of my presentation. There is an entire chapter dedicated to that. Now, as I mentioned earlier, the neural network-based work is only applicable for time invariant systems because time may not lie within a compact domain. And that's why this work, that is adaptive control of time-varying parameter systems with asymptotic tracking, this work is developed, and this is also published in IEEE Transactions on Automatic Control. So let me just start with a brief illustrative example to explain the challenges for developing adaptation laws for an adaptive controller for time varying parameter systems. So let's consider this simple scalar system x dot equals a of t times x plus u, where a of t is a time varying parameter. Now the adaptive controller for this system is given by minus kx minus a hat, which is the adaptive weight estimate times x. And the standard choice of Lyapunov function for this system would be just half x squared plus half gamma times a tilde square, where a tilde is just a minus a hat. It is the parameter estimation error squared. This would be a standard choice. But what happens after we take the time derivative of this Lyapunov function? We get this expression for v dot. Now, if you look at these terms here, minus kx squared term is good because it's a negative term. This term is also good because we can easily cancel this term using our design for a hat dot. So a hat dot could be just gamma times x squared, and it would just cancel this term. Now, if our parameter was constant, that is, if a dot was 0, then we are basically just done with the analysis. But the problem is, when we have time varying parameter, a dot is not 0. And this term is going to just show up in the analysis. And the problem is we cannot even design a hat dot with some robust sliding mode kind of term. That is because a tilde is unknown. So the best thing that has been done in literature is either use some adaptation law, standard adaptation law with some time varying gain, or use robust modifications of standard adaptive update laws, and that only ensures bounded tracking, not asymptotic tracking. Now the question is, how can we design our adaptation law to achieve asymptotic tracking in presence of the time varying parameter? So to explain that, let me just step aside and give some brief intuition about RISE controllers. Let me first explain what's a RISE controller, and also some intuition about PI controllers and how standard adaptive controllers are a generalization of the PI controller. So as we all know, this is what a PI controller looks like. The interesting thing about a PI controller is that the integrator term is actually able to learn and cancel for constant disturbances or steady state errors. So that means a PI controller is probably the simplest form of an adaptive controller. And now look at this expression for an adaptive controller for this system x dot equals y theta plus u. This is how the adaptive controller looks like. So there is a minus y theta hat adaptive feedforward term. But if you look at theta hat is obtained after integrating gamma y transpose e. So this means this is a kind of a nonlinear integrator term. And if you look at this, if the y term is just an identity matrix or just one, then this would actually result in a PI controller. So now let me also tell you about some interesting properties of RISE controllers. So RISE controller is structurally pretty similar to a PI controller. And by the way, this isn't a very rigorous way to state things. I mean, this could also have like damping or terms. So the RISE controller depends, the structure of RISE controller depends on the system, but all of the RISE controllers essentially have the integral of the sign of the error terms. And I'm only focusing on the integrator here. So an interesting property of RISE controllers is that the RISE controller, the integrator in the RISE controller is able to learn and cancel not only for constant disturbances, but also for time varying disturbances, unlike the PI controller. Now the question that I address in this chapter is, what would be the generalization of the RISE controller for the adaptive control case with time varying parameters? So To explain that, let me first introduce the dynamic model, which is an Euler-Lagrange system. So this Euler-Lagrange system terms can be linearly parameterized as yp times theta p, where theta p is a bunch of time-varying parameters. And there is also the tau d term, which is an external disturbance to the system. But even the disturbance term can be considered to be a time-varying parameter. So we can again reparameterize this as the final y theta parameterization with and with tau on the right-hand side. And we also make some assumptions about our time-varying parameter. That is, the time-varying parameter is bounded, so theta is bounded. Theta dot is also bounded, and theta double dot is also bounded by constant. And this is the control design. So for the control design, I introduced the tracking error E1, that is Q minus QD, and based on that, there are filter tracking errors E2, that is E1 dot plus alpha 1 times E1, and similarly, there is another filter tracking error R. And then, based on these definitions, the control input is then designed as YD, which is just the Y matrix, but with the reference trajectory-based terms instead of the actual trajectory-based terms. There is also minus K times C2 term here, which is a standard state feedback term, and there is a mu term, which I'll explain later. But the adaptation law that I design is given by this expression. So theta hat dot is implemented as a projection on this expression lambda 0, where lambda 0 is given by this expression. So we have the learning rate gamma times YD transpose, and there is also this normalization like term that I introduce. And this term is shown to be invertible, by the way, in the dissertation. And then after that, there is a linear in E2 term used in the adaptation law. So this is analogous. This term is analogous to what we have in standard adaptation law. But based on the inspiration from RISE controllers that I mentioned earlier, I also use another beta times signum E2 term here. And there is also a mu dot term designed here. This is to compensate for some of the side effects that are introduced because of the projection operator. This term is only activated when our parameter estimate actually hits the boundary of our set on which we are using the projection operator. So for this controller, I have the main theorem statement, which just says that provided that these gain conditions are satisfied, we are able to achieve asymptotic tracking error convergence. And I will not get deep into the Lyapunov-based stability analysis, but I will just briefly explain what happens in the stability analysis and what I do different in the stability analysis than traditional results. So unlike traditional results, I do not use a half theta tilde square, some parameter estimation error square term in the Lyapunov function. Instead, I use a different approach, which is a P function design. So a P function is, let me first explain what's a P function. So P function could be any term which we can prove to be positive, and the term is also able to cancel for some of the undesirable terms that show up in the Lyapunov-based stability analysis. So this is how I designed for the P function term, and I will actually get more into the P function stuff in the later chapter because there is more interesting stuff that happens with P function in the next chapter. But based on this, then after doing the Lyapunov-based stability analysis, taking the time derivative of the Lyapunov function and doing some bounding, we are able to show asymptotic tracking result. Now I also provide some simulations for this. So for the simulations, I consider a two-link manipulator system with time-varying parameters. And I compare the result with an E-mod adaptation law. E-mod is like a standard adaptation law that has been used in the literature. And we can show bounded tracking with E-mod adaptation law for systems with time varying parameters. And as you can see here, with the developed method, the tracking error is able to asymptotically converge. And the function estimation error is also able to asymptotically converge to 0. And like the previous chapter, gains were obtained using a Monte Carlo-based approach to minimize this cost function. So to conclude, a continuous adaptive controller was developed to achieve asymptotic tracking for time-varying parameter systems. And the developed method offered approximately twofold improvement in tracking, estimation, and control effort. And future work may involve extension of this method for DNNs. There is some stuff that we need to work through that before we are able to do this kind of analysis for DNNs. So moving on to the next chapter. That is exponential stability with rise controllers. So as I mentioned earlier, rise controllers are a class of controllers that have been known for like almost 2 decades right now. But the best known result for rise controllers was asymptotic tracking. But in this work, I'm able to show that the tracking is not only asymptotic, but it is also exponential. So again, a brief overview of what's a rise controller, but I already mentioned that in one of the previous slides. And the best known is asymptotic tracking error convergence. In one of the works, exponential tracking was actually shown, but that was for a very specific application. And also, that result was able to show exponential tracking because that was something specific to the application. But the question that I address in this chapter is, does the exponential tracking result also hold for systems with state-dependent bounds on the uncertainty and its time derivatives? So for that, consider the control objective. I consider this control-affine dynamic system. There is also an additional variable new here. And this variable is something that comes from an external system. And the reason I included this term is to make the analysis more modular. That means new could be something like an adaptive feed-forward term coming from an external system. So this is to make the approach more modular. And again, the control objective is that the tracking error E should go to 0. And then again, the filter tracking error is also defined. This is basically just E dot plus alpha E. I just, for the sake of rigor, I just substituted E dot here. And then we obtain the transform dynamics, that is E dot is R minus alpha E. And the rise-based control input for this system is given by this expression. So D hat is what is important here. So, and note that D hat contains the sign of the error term as shown here. Then D hat dot can be written after differentiating this using this expression. And after some algebra, we are also able to show that the filter tracking error R is also D minus D hat. So filter tracking error is also kind of, it is also a disturbance estimation error. And the interesting result that I'm able to show at the end is that not only is the tracking error convergence exponential, but also the disturbance estimation error that is also able to exponentially converge to 0. That means we are able to exponentially identify the disturbances. And this is also something that we used in one of the papers that I co-authored, where we construct a rise-based disturbance observer that is for adaptive safety. So the closed loop error system can be rewritten in terms of these two expressions. where n tilde and nb are some bucket terms designed as follows. So n tilde is a set of terms that can be bounded using a mean value theorem based inequality. So that gives us state dependent bounds on the term n tilde. And NB is the set of terms that can be bounded by a constant. And we also make some assumptions on the auxiliary variable nu. So that is, nu is bounded by a constant, nu dot is bounded by a constant, but nu double dot has state dependent bounds. And I also give an example of a system that satisfies this assumption. So for example, nu could be a dynamic neural network given by this expression. That is projection applied on this neural network term. And after doing some analysis, you could show that this dynamic neural network satisfies the stated assumption. And based on this, we are able to bound NB, the term NB using a constant, and the term NB dot could be bounded by a constant plus these state-dependent upper bounds. So now coming to the Lyapunov function design. So this is where the contribution was, this is where I developed new technique to show the exponential tracking result instead of just asymptotic. And this was done using a new design for the P function. So the P function here is designed as a solution to this differential equation. And in the previous results, the P function design would have all of these terms except this minus lambda P times P term. But what I did different was I also introduced this minus lambda P times P term. And this term was the only term that was required to show that the convergence is not only asymptotic, but it is also exponential. So this looks like a pretty straightforward change in the design, right? I mean, I just added one extra term to show exponential tracking. No, wait, there is more to it. We also need to ensure that P still remains positive for all time. And that's where the contribution is. So the way we can do this, we can first solve this differential equation. This is by noticing that this is actually a linear system in terms of P. So there is P dot and there is minus lambda P times P. And the rest of the terms here can be considered as an external input to this system. And since then, this is a linear system, we can actually solve for this system. And after solving this differential equation, we get the following expression for P. So this involves some convolution integrals showing up here. But given this expression, and provided that the gain conditions alpha greater than lambda P and beta greater than these terms are satisfied, we can ensure that P remains positive for all time. Now, to state the final theorem statement for this chapter, I introduce these terms, and then W is a function defined as shown here. And after defining this, we can show that the zero solution E comma R equals 0. This is our equilibrium point. This is semi-globally exponentially stable in the sense that we get this exponential result, provided that the previously stated gain conditions and also this gain condition is satisfied. So for future work, we can do extension for for systems with unknown time varying and state or input delays. So some of this is already ongoing work, and one result was also published in a conference for this. And extension can also be done for systems with input saturation. So moving to the final chapter, which is the conclusion of my dissertation. So this dissertation provided the first results on Lyapunov-based adaptation laws for fully connected DNNs and ResNet-based adaptive controllers. This dissertation also provided the first result on adaptive control for time-varying parameter systems with asymptotic tracking error convergence. And this dissertation also provided results on exponential stability for RISE controllers. So now let me discuss what opportunities this dissertation provides for future work. So this has opened up a lot of new open problems that could be solved in future. So to begin with, concurrent learning-based adaptation laws can be developed for DNNs. So concurrent learning is an adaptive control strategy that has only been developed for linearly parameterized systems. And what that technique is able to show is it can show parameter convergence with the adaptive controller under finite time excitation condition. But DNN is a highly nonlinear parameterization, and this has not been developed for nonlinear parameterization such as DNN. So developing concurrent learning-based adaptation laws for DNN is an open problem. In future, we can also develop neural architecture search methods for adaptive control algorithms. So this is an ongoing work in collaboration with Dr. Yu Wang. We can also develop adaptive controller based on recurrent neural networks. So the results developed in this dissertation were only applicable for feedforward DNN architectures such as ResNets and fully connected DNNs, but it is not applicable for recurrent neural networks. So this is also an ongoing work. Emily is working on that. We can also do indirect control or adaptive backstepping with DNNs, and this could be very useful for problems such as robot herding. So Christian's working on that right now. We can also develop adaptive control results for physics-informed deep neural networks. The reason I'm saying this is because the results developed in this dissertation are only applicable for complete black box models such as the DNNs, but it would be better if we can leverage some knowledge of the physics of the system into our DNNs. So Becca is working on that right now. And in future, we can also do adaptive optimal control with DNN. So we did not have any optimality guarantees on our DNN-based adaptive controller in this dissertation, but this is an interesting problem that I am interested in exploring in future. Moreover, the results developed in this dissertation were not applicable for stochastic and discrete time systems. The system that we considered in this dissertation was a deterministic continuous time system. But I'm definitely interested in exploring that for stochastic and discrete time systems. In future, we can also explore meta-learning based adaptation for adaptive controllers in general. So let me explain what this means. Meta-learning basically means learning how to learn. And this is something I'm very interested in. So what we can do is we can use another neural network to actually learn the adaptation law. And this is something that I'm working on in collaboration with Dr. Pramod Khargonkar at UC Irvine. Additionally, as I mentioned earlier, RISE controllers for systems with input saturation and delays can be explored in future. So yeah, these are my ideas, and I'm also open to ideas from you guys. So once again, thanks everyone for attending my dissertation defense. I really appreciate you guys took the time to come here. Thank you. And now I can take questions. Yes. Yeah, I mean, the activation function, we can pretty much use any activation function. It has to be continuous. Yeah. So in the second chapter, I actually do some non-smooth analysis for activation functions that are not differentiable at some points. For example, the ReLU activation. ReLU is continuous, but it has discontinuity at 0. So, and I do the analysis for that in the second chapter, but I skipped that in the ResNet because it is kind of redundant. That's not the main contribution of that chapter. So, yes.
Good job.
Thank you. Yeah, let me just check this chat. I'm not able to hear, I won't be able to hear from the Zoom. So if there are questions, please type. Yeah, any more questions? Yeah, sure, of course.
For your, I think it was your RISE DNN controller. What was your domain for semi-global stability? Like your state domain? Is that like a domain on the initial state? Is that how that works?
Yeah, I mean, basically we have state dependent, the initial state dependent gain condition there. So let me just, like for example, this. So there is some rho function, but this is a function of our initial state. So the idea is to select our gain condition based on our knowledge of the initial condition. And if we have that, we would always get exponential convergence. Yes. I don't see any new questions there. Yeah.
I was interested in the part about the vanishing gradients, how you fix that.
Yeah.
Why were the vanishing gradients happening in like a traditional fully connected net?
Yeah, let me just go back there.
Because of like the air going to zero?
Like some of the terms that show up in the expression for the Jacobian, those are near 0. So, and we have a product involving all of those terms. So the result would be even smaller. So like, for example, like see these expressions that these products that show up in the expression. So now let's say that we initialize V hat with 0.1, for example, and there are 10 such layers, so K is equal to 10. So what would that mean? We would have 0.1 being multiplied 10 times in this expression, and the result would be 10 to the power minus 10. Yeah, exactly. Yeah.
The weights might want to change signs.
Yes, that's the sign is not a problem, but just the magnitude is the problem here.
Weight times errors. Can it not also be a function of small errors?
Which error are you? The tracking? I mean,
You're multiplying two things. You're saying that if one of them is small, that's a problem. But I mean, can it also be that the errors are small and that's also a problem?
well, I mean, if our errors are small, then typically we don't even require adaptation because, like, I mean, the tracking error is 0, then we are not even needing to learn the DNN. I mean, the controller is already stabilizing this.
In subsequent section.
Okay, cool. Yes.
So like the DNN based.
Yes. I mean, main thing is like whether the universal function approximation holds for that. That's the first question we need to look into. I mean, that would require like modeling a time varying function in terms of DNNs with some time varying weights, and how do we establish that? That's a question I don't have an answer to, so we can explore that in future.
Thank you, everyone, and you're welcome to grab some food on the way out quickly.
I'll also stop recording.